All right, now we're going to look at 11.2 probability problems with events involving not. So we're going to talk about the probability of a complement, or that would be the idea of not E. So if we kind of back up and look at a Venn diagram for a minute, this Venn diagram for chapter 11 we've called S for the entire sample space, or every single possible way a task can play out. Some particular event E sits inside of the sample space. The space outside of E, but inside of S, we call E prime, or not what's in E. So here's what we know. We know that the probability of E plus the probability of E prime will equal the probability of the sample space. And don't forget, P of S is always equal to 1, because if anything in the sample space is allowed to happen, then you're always going to have success. So this idea of the complements principle says the following: the probability of not E, or that's E prime, is equal to 1 minus P of E. And we're going to learn with some of these problems that sometimes this indirect approach is easier to find our answer than doing it directly. So for the experiment of rolling a single fair die, find the probability of the following events: not less than 2. Well, let's look at our sample space. For a single fair die, we have 6 numbers. And I want to know the probability that I am not less than 2. Well, the complements idea says that I would do 1 minus the probability that I am less than 2. So 1 minus, the reason why this is 1 is the biggest probability can ever be is 1. If we subtract the probability of what we don't want to happen, the answer will be what we want to happen. So the probability of less than 2 is the complement of not less than 2. So things less than 2, well, just the 1. So the probability that you're less than 2 is 1/6. If you subtract that, you get an answer of 5/6. Now, it is absolutely the case with this example that you could have just looked at what's not less than 2. 2, 3, 4, 5, and 6, and gotten right to 5/6. But we're practicing this complements principle idea so that when we get to harder problems, we are understanding its approach. Okay, so now it's the probability of not prime. Well, that equals 1 minus the probability that a number is prime. So this is 1 minus. Remember, a prime number is a number only divisible by 1 and itself. Also remember, 1 is not a prime number. So the prime numbers are 2, 3, and 5. So we would say 3/6. So 1 minus 3/6 is 3/6, or half of the numbers are not prime. Now again, you could have directly looked at it and said 1's not prime, 4's not prime, and 6 not prime, and gotten a right to 3/6. All right. Now let's say the experiment that we're going to run is drawing a single card. Find the probability and the odds in favor of not drawing a 7. Well, if we want to figure out the probability of not a 7, we could do 1 minus the probability that we get a 7. Well, how many 7s are in the deck? There are 4 out of 52. So that leaves us 48 out of 52. Remember, fractions should be reduced. We'll divide each by 4 and get 12/13. Remember, if you want to get to odds in favor, this is always A over A plus B. And odds in favor is looking for the ratio A to B. Well, A is 12. And B is whatever you have to add to 12 to get to 13. Well, 1. So our odds in favor are 12 to 1. All right, if the probability that Dwayne will get an A on his Math 111 test is 0.18, find the probability that he will not get an A. Well, the complements principle says if we want to figure out the probability of not an A, we do 1 minus the probability that you get an A. Well, they tell us that. It's 1 minus 0.18, so we get 0.82. How about suppose we want to form 3-digit counting numbers using the set 0 through 5. Find the probability when selecting a number it will not be a multiple of 10. Right, so the probability that you are not a multiple of 10 would equal 1 minus the probability that you are a multiple of 10. Okay, now to do this one, we have to incorporate the fundamental counting principle. So to make a 3-digit counting number, it's always a 3-part job. So we're going to do the denominator first. Remember, the denominator is just the job, no conditions. So the job is to build a 3-digit counting number using these numbers. Well, any of these 6 numbers can go how it ends, how it is in the middle, but only 5 of those numbers can be in the front. That's because when you start a 3-digit counting number, it cannot start with 0. Now the top is this condition right here. We want a 3-digit counting number that is a multiple of 10. So it's still 3 parts because we haven't changed our job. It's still a 3-digit counting number. We still can't use 0 in the front. We can use anything in the middle. But to be a multiple of 10, you must end in 0. So there's only one way that can happen. Now to save me time with my calculator, right here I can notice that these 5s are going to drop out and these 6s are going to drop out. So I get 1 minus 1/6, or I get 5/6 is my answer. All right, now we're back to the golfer Amy Donlin and her possible likelihoods of scoring certain scores in golf. It says, in what given round, find the probability of Amy scoring not in the 70s, 80s, or 90s. So we want the probability of not 70s, 80s, or 90s. So that equals 1 minus the probability that it is 70 or 80s or 90s. So it's 1 minus, now be careful. We learned that or means addition, so we're going to have to add a bunch of stuff together. So it's going to be 0.30 plus 0.23 plus 0.09. Notice what I'm grabbing. I'm grabbing all of the probabilities of the 70s, 80s, and 90s. So 0.30, 0.23, 0.09, 0.06, 0.04, 0.03. Right? You're going to add all that up with your calculator, and you're going to subtract it from 1, and you get an answer of 0.25. Now that was the indirect way using the complements principle. Another way that you could have simply done this problem is realizing that if you don't score in the 70s, 80s, or 90s, you must score below 60, in the 60s, or 100 or above. So you can see that those numbers also add to 0.25. This would be 0.04 and 0.06 is 0.10, plus 0.14 is 0.24, plus 0.01 is 0.25. So you could have just directly went after that problem also. How about a 2-card hand? What is the probability of holding at least one ace? All right. So now we're going to get back When we did chapter 10 problems with at least, we used AU and A complement. So we're going to kind of do it that way. So P of E is what I'm looking for, right? P of E is 2 cards at least 1 ace. P of S is always equal to 1. And P of E prime is equal to 2 cards, no ace, because it has to be the complement of E. So if E is at least 1 ace, P of E prime must be no ace. So if we want to find P of E, and we need to use P of S and P of E prime, we're going to subtract. So we're going to take P of S minus P of E prime. So this is 1, and this is a fraction we have to find. Now remember, we're dealing with card hands, and every time we deal with card hands, we use a combination. The bottom is any 52 cards, I need 2. Remember why combination? Because we're not allowed to repeat. Every card's unique, and order doesn't matter how you hold them in your hand. Now the top is still 2 cards, but no aces. So it's still a combination. It's still 2 cards we need in our hand, but we're going to remove the aces. So 52 cards will go down to 48. This will be 1 minus 0.85, which now equals 0.15. All right, a couple more here. A shipment of 12 microwave ovens contains 4 defective units. A vending company has ordered 4 microwaves, and because each is identically packaged, the selection will be random. Ooh, key word right there. Find the probability that at least 1 unit is defective. So P of E equals 4 units at least 1 defective. P of S is 1. P of E prime is 4 units, no defective. So if we want to figure out the probability of E, it is much easier to determine the probability of 4 units, no defective, and subtract from 1. Because this has so many choices. 4 units at least 1 defective means 4 units with 1 bad, or 4 units with 2 bad, or 4 units with 3 bad, or 4 units all bad. There's a lot of work there. This is 1 step, subtract from 1. So this is 1 minus P of E prime. So we're going to draw out a fraction bar, and we're going to do the top and the bottom. Now I said this random idea was a key word. Random usually means that order doesn't matter and repeats aren't allowed, so we're going to use a combination. The bottom is just the job. The job is a company ordered 4 microwaves. So this is all 12 microwaves, give me 4. Now the top is still give me 4, but I don't want any bad ones. So right here it says that it contains 4 defective units. Well, if I want 4 units no defective, that could also be said 4 good units. Well, there are only 8 good units, so I'm going to do 8C4. When you find this with your calculator and you subtract from 1, you get 0.86. All right, last one. The last one's going to use a new phrase that we kind of have to pause and talk about for a minute. So for the experiment of drawing a single card, find the probability that it is neither a spade nor an 8. This phrase neither nor has to be done a very particular way. So we're going to pause here and we're going to learn this new definition. So this is how to handle neither nor problems, right? The probability of neither A nor B is found by doing 1 minus the probability of A or B. So let's break this problem into steps. So step 1 is to find the probability of spade or 8. Now when you do an or problem, you have to ask yourself, can those occur at the same time? Can you draw a card and that single card is both an 8 and a spade at the same time? Absolutely, the 8 of spades would satisfy that. So this is going to be the probability of spade plus the probability of 8 minus the probability that you are the 8 of spades. Probability of spade. There are 13 spades and 52 cards. Any of them would work. Probability of 8. There are 4 out of 52. Minus 1 out of 52 because there's only one 8 of spades. So this is 16 over 52, which we are going to reduce by 4 and get 4/13. Now remember, that's the answer to an or question, but this was a neither nor question, so step 2. So step 2 says the probability of neither spade nor 8 is equal to 1 minus what you just got, because it says 1 minus the or part. So you're going to take 1 minus 4/13 and you're going to get 9/13. So this would answer the neither nor question.